In this video, we'll be introducing the concept of motion and describing motion using something known as a displacement graph. To start us off, let's just define the idea of motion itself. Motion is an object's change in position relative to a reference point. Now, we are familiar with the concept of motion. We see things moving around us all the time, and that is based on our reference point. Where we are standing, something is changing its position relative to us. But that motion can change if we pick a different reference point. So for example, this astronaut here shown in this picture is moving relative to the Earth really fast, over 17,000 miles per hour. But relative to the space shuttle, where this is being taken, the picture is taken, they're not moving at all. That they are moving exactly the same speed as the space shuttle. So relative to that position, they're not moving. They're not changing how far away they are from that place that the picture was taken. So we are typically going to define our reference point as us, the observer, where we are standing. But this might change as we go throughout. Distance and displacement are two words that sound really similar to each other, but they have a couple distinct differences that we care about in terms of physics. Distance is how far you have traveled. If you have an odometer on your car or your bike, or you're counting your steps with a Fitbit, you are measuring how far you have traveled. Now, you can run laps around the house. It is going to measure every single step that you take. Distance is a measure of how far you are from the origin. Basically, it's a way of just looking at the beginning and the end and measuring how far you went overall. Doesn't matter what path you took to get there. Now, we can see this on a map. The distance as the crow flies is the displacement. So if I were going to go from Minnetonka High School all the way to Niagara Falls, in the end, I could draw a straight line from Minnetonka to Niagara Falls. That would be my displacement. That's how far I am from the origin. My distance, how far I traveled, is really dependent on the roads. That the roads here have to take me down below the Great Lakes, and I can measure that overall distance by tracing out exactly where I drove. I can see that the distance as the crow flies is less than the distance by land. So my displacement, how far I am from the origin, is usually going to be a smaller number than the distance, unless I'm able to take a straight line path all the way there. We can see this in a simpler form in this example. You walk 5 kilometers east, so something that looks like this. You turn around and you walk 2 kilometers west. So you go back from 5 over to 3. You turn around again and walk another 4 kilometers east. What's your distance? What's your displacement? Again, distance is how far you have totally traveled. So we go 0 to 5, 5 to 3, that's another 2, 3 to 7, that's another 4. So my overall distance is 5 plus 2 plus 4, or 11 kilometers. Now my overall displacement, all I care about is where I started and where I ended. My starting point to my ending point is 0 all the way to 7. My displacement is just 7 kilometers. Displacement is how far from the origin. Distance is how far total I've traveled. I can show this on a graph as well. The only difference here is I'm going to have two different axes, and I'm going to incorporate time here. Right now, I'm just going to draw time as I see fit. No particular time gradient here. Sometimes in this graph, we can change position into displacement. They mean essentially the same thing. So if I started at 0 time at position of 0, and I go 5 kilometers east, then I turn around and I go 2 kilometers, so I go back from 5 to 3, and then turn around again and go up to 7. That's the same thing I did on the last slide, only now I'm showing it in terms of time. And I can show the same going up 5, back 2, up 4 to get 11 and 7. Another way that we can show this changing of position is something called a stroboscopic photograph. In this case, basically, we're taking lots of exposures of some sort of moving object. In this case, it's showing the soccer ball every 0.04 seconds, and we can see where it is in that given amount of time. Well, the nice thing here is every exposure, every picture that's taken is taken over the same time interval, which means that if it's moving really fast, we expect longer distances in between those pictures. Basically, if you are opening your eyes every second, something that's moving fast is going to move farther each second. Where it's moving slowest is where the objects are closest together. And we can see lots of cool examples of this used in sports, but we can also use this idea to see if something's moving at a constant velocity or changing its velocity. So here I've got this billiard ball that's rolling down, and we can see that's pretty much a constant interval that's being shown there. About the spacing is the same overall, every single picture that's taken. Where over here on the right, I see that it is accelerating. It is moving faster each second, so every picture that's being taken is showing a larger increase in its position as it's falling down, which we know is something typically that's speeding up. So more spacing between pictures, moving faster. If it's changing, it's accelerating. So if I were to draw this as a graph, but also as a stroboscopic photograph, I can describe a lot of different ways of motion. So first, it's something really simple, an object not moving. Let's place it here on the 4 in its position and just show where it is over time. Well, it's always on the 4. So as we're increasing our time, we're never really changing its displacement, showing displacement on the y-axis. So my constant displacement, an object not moving, is just a straight line showing me where it is, 4. If it was at the 2, I would draw a straight line at 2. If it was at the 6, I'd draw a straight line at the 6. The same thing all around. Now, if I had an object that was moving forward, its displacement, its position is changing. So I can see it moving forward here, and every second I draw where it is in that split second in time, and I can see that I'm creating kind of this upward trend, that every second I went one spot farther in its position, so I can draw a line that looks something like this. So an object moving forward is this straight line, in this case for constant velocity, moving upward as the displacement is getting bigger, so a positive slope. I can also show an object moving backward. Let's start it out here at 7 and then drop it down all the way to 0. And we can see that as the time increases, the displacement decreases, which gives me an overall trend here that's negative, a slope that's negative going down. I can also use this to compare different objects that are both moving in the same direction. So here, if I show you what's going on, this red ball is obviously moving slower than the green ball. It's actually moving half the speed. Well, let's split them up here and graph them. This red ball, every second or every picture is moving exactly 1 meter forward. I saw that graph earlier. Now let's graph the green one. Every second, the green one moves 2 meters. So we can see how that tracks. I am actually not able to get quite as many pictures in because it made it to the end faster than the red one. But I can see that slope looks different. It's a steeper slope when it's moving faster because it's covered more ground per second. And if I wanted to, I could actually calculate the slope. Here I can find a slope rise over run, 2 meters in 2 seconds, gives me a slope of 2 meters over 2 seconds, or 1 meter per second. The green one's 2 meters for every 1 second. That's 2 divided by 1, or 2 meters per second. We'll talk more about slope later on, but the slope here on these graphs tells me the velocity. 2 is faster than 1. The steeper slope is faster than the shallower slope. I can also show something that's speeding up. So in both of those cases, it was moving constant, a constant 2 or a constant 1. But if it's speeding up, I'm going to see a bigger and bigger spacing in between pictures. If I track this out on a displacement versus time graph, I see that the distance that it travels, so this vertical part, gets bigger and bigger for the same time interval. And I get this nice curve where it starts pretty shallow, pretty flat here, and then as it speeds up, it gets steeper and steeper. So just as we saw, the steeper the graph is, the faster it's moving. Well, as it speeds up, our graph gets steeper, which means it's a curve. I can also show an object slowing down. Still going forward, it starts going really fast, so a large spacing, and then as it slows down, that spacing gets smaller and smaller and smaller. So it starts out with a large slope, and as it slows down, that slope becomes closer to zero, basically flattening out towards the top. So we can see that these are similar. They're both curves. The way that we know which is which is if it is, so when the velocity changes, the slope changes and the graph is curved. The way that we know which one is which is we can look at this one here is speeding up because it is getting steeper, and this one here is slowing down because it is flattening out. So that's the biggest difference. But if we know the velocity is changing, if it's getting faster or slower, we expect this to be a curved graph. So these graphs that we're looking at, they tell us a story that if we have a graph that shows us over 16 seconds where something is, it goes from 0 to 5 to 7, stays at 7, down to 4, down to 1, down to 0. This graph tells a story. Let's look at the story that this graph is telling. So in this particular graph, let's split it up into these 5 different segments. Going from 0 seconds to 3 seconds, I know that I have something that's moving from 0 to 5 meters. So let's start our little guy here at 0. He's going to move all the way to 5 meters. All right, that's the first part of this graph. Now, he's still going to be moving forward. He's going to go all the way to 7 meters. But you notice how the slope is changing? That means he slows down. So whereas he did this first part pretty fast, this next part, he's going to go a little bit slower because the same amount of time, he just doesn't travel as far. Now, from B to C, this green part, he's just going to be chilling here. He's not moving for 4 whole seconds. And then once he gets to C, he's going to start moving backward, going all the way back to 4, and he does so really, really quickly. It's a very steep slope. And he keeps going backward, just a lot slower to get all the way to the end. So this graph tells us a story. If it's going up, it means he's moving forward. If it's going back, it means he's moving backward, going down. I can see another story here. Let's say that my displacement of 0 is my house. I could have a scenario where Bob leaves his house and walks to his friend's house. Now, on the way, he stopped for gas, buys a snack there. So he didn't make it all the way to his friend's house. He stops there, buys a snack. But then he realized he didn't have money, so he had to walk all the way back to his house to get some money. And then he ran back to the gas station. So he went to the same position here, same height as that red line, but notice how it went steeper than the first time because he ran. He went faster. And then he stops to buy a snack, and then he continues to walk to his friend's house, which is somewhere up here. All right, so in this video, you should be able to describe the difference between distance and displacement, how far the crow flies, or how far overall you've traveled. You can calculate distance and displacement for one-dimensional motion, moving backward and forward. You should be able to calculate or plot a constant velocity on displacement versus time, something that's going forward or something that's going backward, and then plot the changing velocity, this curve on a displacement versus time graph, and be able to recognize which graph is which and what those pictures should look like.